Good afternoon. Um, it's interesting. Ed made my life very easy. He said, we are only looking at quantum computers from a practical point of view. A lot of conversations takes place on quantum computing. It's all about chips, circuits, qubits, whatnot. But I am actually a quantum physicist, but I spend more time trying to do business. And is there really an application of quantum computing in major industries? And if we want to see the growth, um, when quantum computers will become really what I call mainstream is when it actually solves a real world case. I think that case study was pretty close, but there are a lot of challenges in building such systems. So I'll talk in terms of energy. Last 10 years I spent as a technology fellow and chief data scientist at Halliburton. Before that at a consumer company, and before that at internet building AI algorithms in 2005 and so. And so we'll talk about in energy and just like COP28 just got over, and energy transition is on a topic of importance. And I think this is where um, I feel that if a, if a proper case study is done, we could really win. But because everything depends on energy. In fact, I, in the conference, a lot of work is talking about quantum computing, but nobody is talking about its implication to emissions. Right? Already people are studying how much cloud computing is generating emissions, but the quantum computers are also going to be contributing to it. So there's a checks and balances that needs to be for us to worry about. So what should be our strategy and how do we really get a quantum advantage in the energy industry? So I'll discuss few things, basically talk about what energy disruption looks like, what are the key challenges, how do we really create exponential value, and then what's the path forward. So if you look at what the challenges, it's a very interesting challenge for, they call the energy trilemma. You want energy to be really affordable and sustainable and secure, right? And that is almost impossible. If you are a physicist, these are like three cogs that are connected to each other. You rotate two, the third one will make it stuck. So if you want really sustainable energy and secure, your cost becomes higher. And if you make it affordable, then you probably don't have sustainability. You will lose one of the other, but this is the need for the hour. And then whole discussion on energy transition takes place as if we are going to replace. Energy transition means replace from current fossil fuels to something else, whatever it may be, renewable. But can you really do it in practical sense? Currently, the world uses something around 8,000 million ton equivalent of oil and gas. In order to replace that, you would need something like 800 nuclear power plants of the largest size. You would need largest scale hydroelectric stations, pretty much. You would need billions of solar panels and millions of uh, uh, other things, hydrogen, geothermal, and other. Where is the workforce for all of this? Where is the technology for all of this? Right? Each one of them have significant optimization problem. I think if you have read the news, Australia has deployed solar panels 35 years ago. Now they are at the end of their life. We have no good mechanism to dispose them. So we have a different problem. So we can try to get rid of fossil fuels, but do we know the life cycle of these and the impact to the environment for these? And each of them, I can tell you, has significant optimization problems even today. Where do you put the windmills? In what orientation? Under what conditions? So these are just interesting challenges. Uh, right? Yes, 2 days ago when the COP got 28 got over, they talked about that we need to triple our energy productions to 11,000 gigabytes from renewables. Right? Double the efficiency. Now, where does how do you improve the efficiency? It's very good to talk at the high level, big numbers, but doing it is hard. Methane reduction, look at that. 70% we can reduce by current technology, but there is still understanding gap. 30% requires new technologies. Now, which are new technologies? In this case, we're talking about quantum and others. So, in some sense, fossil fuels are not going anywhere. And I think this was a statement made by ADNOC CEO, and he got really, people bombarded him with lots of questions. But that's the reality. And the reality is it gets even more complex. This is how the landscape looks like of energy at some point. And if since we are talking about optimization problems, oh, this one. Just look at the three variables: energy source, consumption, and the maturity of energy transition in a different environment. Which country, which city, which organization will fall in which local minima? We don't know. So taking an example of how this, let's assume that if this particular conference center was really optimized, will that actually model work for the whole city? Probably not. And that's the challenge. So it's a significant what do you call optimization problems that can be really addressed, and that requires quite a bit of data that really need to address few things. One, whatever results we do, they need to be done much faster. Anything that we do in energy spectrum, we have to actually calculate the emission impact. Doesn't matter whether it's a cloud infrastructure, whether digital twins, or any other method that we use, traditional ones. And then this requires a completely new kind of thinking. How and what kind of thinking we are talking about is actually im- implementing some of the fundamental challenges to the technology, basic technologies, and then enabling data and AI. I think Ed was giving an example of data science on fuel consumption for jet plane. That is just one example. Similar example exists. Same problem happens when we are moving LNGs around the world. It is consumption is significant. How do we reduce that, right? And I think the only way we can really transform this industry, energy industry, is by really leveraging quantum computing and blockchain. And why is it important? From a money point of view, there was an article a couple of years ago which says that oil and gas industry has, if the laser is working, I can't see. Okay. I don't think it's working. Okay, it doesn't matter. So if you see that for 20 years, roughly significant capital has been invested, and if that amount of money is invested in technologies, that can be significant. And if you look at the in general, the whole of energy industry is nothing about. It's all about understanding the art and science of basic particles. So whether it is hydrocarbons, whether it is solar, whether it is wind, if we can understand at the atomic level, I think we can really make a difference. So boil down all this big high level things into three areas where we can actually take advantage. The complexity will remain really unlimited. What industry needs is real-time optimization, not because when you are, for example, when you are extracting oil, it's real time. Anything that goes wrong, you can really lose money fast. Same thing happens when you're consuming, right? Like the jet plane example that Ed was giving. When you're moving, LNG is significant. Same thing happens with wind. Wind pattern changes. Windmills don't become efficient. How do I actually address? So these are real time optimization problems. And then, of course, eventually you need to build something like more innovative solutions. So in some, where does quantum play? Right now, at least, right, in fossil fuel industry, we can really do small toy cases for building algorithmic materials. Right, these are important where in various areas, whether it is related to coatings, whether it related to leak detection, you can actually look at those kind of things. Of course, high HSE safety is very important, and then in the production cases. And of course, one of the most case study I'll talk about, how do I reduce time to find actually oil? And then eventually, you can actually optimize this energy mix, the diagram I was showing earlier, and algorithmic materials will actually play a significant role, which is, I think, in the morning there was somebody talking about proteins, etc. And those kind of taking that not to proteins but to other materials, those kind of things can be implemented in the other energy sectors. Furthermore, one can actually do these kind of things in reservoir characterization by building what I call effective Hamiltonians, and that actually can change the way we do things. And then we also can do innovative solutions by literally looking at fluid dynamical equations from a variational principles. And these things, in theory, have been done. Now that it's time for them to be done computationally. So one case study in simple terms, not going in details, uh, basically surface to reservoir, like surface is this, and think of under the stage is the oil. Just to find that takes a long time. You do what is called seismic study, you create sound waves on that corner, you capture them on this side, and then try to figure out what is underneath, right? And that seismic analysis takes like years for sometimes to really figure out how much oil is under this stage, right? So it's basically spectral decomposition, greedy wavelets. Any algorithm that you can think of has been applied over the last 60, 70, 80 years. But they are very compute intensive, generate significant amount of data eventually, and still uncertainty remains high, very high uncertainty. And in noise to signal ratio, we want to keep reducing. But by doing certain aspects of quantum transformation and applying quantum and machine learning together on that large volumes of data that has been created, one can actually reduce this time from 50 to 70%. So in some sense, there is applicability, and these use cases have to be built one at a time, and eventually one really, at least in energy sector, one has to really start leveraging different kind of computing technologies together, attach them to what is called natural simulations, and eventually build a quantum platform. So this is a different platform than just doing a chip kind of a platform. So in summary, I see real practical use for quantum computing when we build a platform that can integrate our various aspects of energy, and eventually I think we can win. So what we can do is, energy industry basically faces compounded disruption, and quantum computing can save. Energy mix will always remain complex, but disruption is a must. Every industry must go through disruptions. This is an example from India. Human beings disrupted environment for elephants, and now elephants are disrupting our life. Many of these things, uh, some of these things have been written by me in various articles, and some are new. Thanks very much.
Questions out there? I'll go ahead and, oh, here's a question.
So when you mention disruption there, you talked about machine learning and quantum, and so it sounds like you're referring specifically to computational improvements, which have taken their time. It's a slow evolution of those. So it's not really a disruption. Is there something bigger you're thinking about? Like, is
Yeah,
there,
so
yeah.
the overall disruption, I'm thinking much bigger, right? This is just one example for one particular use case. But the goal is uh, when we are really talking about energy transition or energy mix, that requires integrating not only the smart grids which are generated by renewables, smart grid which is currently existing, uh, and then these things have to all come together and talk to each other. Right now, companies that are doing electricity, they are doing electricity. The people who are doing solar panels, they are doing solar panels. It's not integrated, right? So you can put a solar panel in California and connect it to your electricity, but that's at an individual level. But if we are talking about an industry scale or a locality scale, that requires a different kind of connectivity, and that is where the disruption will take place. and that's where the actual value comes in. Because you remember, you when you put PV panels on your roof, you are not really worried about any other things. Okay, I got a nice deal, that's what it is. But when disposal comes, who's going to worry about those greenhouse gases that you are going to generate, right? So we have to look at a bigger picture, right? And the consumption, the numbers that I showed you, 8,000 million tons equivalent, is with the current population and current usage pattern in the world. We all know the population is increasing. Our hunger for energy is increasing, whether it is US or whether you can talk about developing nations. All of us are increasing. Even US is not reducing its energy consumption per person. So imagine that how much energy we need extra. So that and hence that disruption is very important for us. And I think the disruption will come from a combination of new materials that can be put on these equipments, reducing the leak detection, reducing the gas detections, uh, right? Leveraging different kind of fuels, biofuels, etc. And this, if you look, that's why it's a very complex picture in energy.